Let's change the camera to this one, the huddle cam. And then you want to, yeah, no, use this. Okay. So you want to set this. So for example, let's first move this. Yeah, let's set from the front side. Okay, what we can do is that's where the remote is. That's okay, but we'll turn it around. By the number. Like, right? New ground. They're back. Okay, so we don't use it. Use the remote without the remote. Is it possible? Let's see. Let me.
Yeah. Should I press record on here or? Oh,
It should be automatically recording.
oh, perfect.
Yes, probably. Yeah, this should be sufficient, right?
Yeah, it should be good.
Okay, let's see. If it is too tiny or something, we should go. Hello, yes.
So the two of you feedbacks on Wednesdays, what time for that?
It's at 4 o'clock. Wednesday at 4 o'clock.
Okay, thank you.
Okay. Maybe I should make announcement on that. Hello, good morning. Sorry about the delay. Hopefully this will be more streamlined next time. This is getting recorded just for your information. So if you want to be aware of that. Yeah, just now there was a question about what time is the tutorial session for this course, which is 206B. And I can say that there was no enrollment, or there is no enrollment as of now in that. So last week the class was not held. So if you are wanting to attend that, at least let me know so that I come to the class. So that since there was no enrollment, I never showed up in the class. So if there is any interest and if you enroll, then I will of course know. So most probably there's a good chance that it might be canceled. At least on my list of courses, it did not show up. So be aware of that. But if you're interested, it can be open. So let me know in case you're not able to enroll. Yes. It is possible to be, yes, it is possible. Yeah. As far as there are few people in that and everyone is fine with it, yes, it should be possible. Yes. Correct. Yeah. Okay. Yeah, the answer is yes, the time is flexible. If that is the only thing stopping you from that, then that can surely be considered. Yeah. Okay. Especially if there is no one in the 205B, that is sorry, 206A, the other the one that you have already completed, there is one student in the in the class, so it's kind of personal tutoring in a sense. So if there is only one person, I don't mind adjusting the time to the person that it works with. That's for your information. Okay. The homework one due next on Thursday, and we are lost 15 minutes over. So let me change the date because I'm afraid that I will not be able to finish what I want to do today. So when is this 8? So it's September 6th, Tuesday. Okay. Too many changes at the last moment, but any confusions on that? Any comments? Okay. We introduced the idea of Coulomb's law, which is basically the law that governs the electric force between anything that has a charge on it. Remember, gravitational force is a force that acts on anything that has mass on it. In general, if you have two materials that have masses, they interact using what is called the gravitational force. And any two quantities that have charge on it, electric charge on it, they interact using they interact through electric forces. And we introduced introduced Coulomb's law, which is the electric force. It's often sometimes called electrostatic force, but more electrostatic force. It means to say that whatever we are doing is mostly true only when the charges are at rest. When they are moving, there are other effects that come in, and this is only an approximation to what happens during the dynamical case. So this is Coulomb's law. So okay to say there's electrics, there's static coordinate, electric force, then the charges are basically at rest with respect to each other. We said based on whether it is positive, negative, or zero, we have the electric force given by electric force on charge 2 by charge 1 on 2 by 1, and that's equal to a constant K. It is related to the permittivity of our vacuum. It is 1/4π naught. So this is Q1, Q2 over the distance between them. It is R squared, and the direction R hat. We have this to be the charge Q1, and that's charge Q2, and idea is connect a line from the center to center, from the surface to surface, and this is a direction along the line connecting them. That's our hat, and going away from point 1 when I'm talking about force on 2 by One, I want to draw a line or a direction along the line connecting the two charges and then going away from point one. And if both are positive, the electric force is acting away from one. This is F1. And its magnitude is inversely proportional to R and linearly proportional to the charge itself. That's the idea. Is one of them was negative, then it is attractive. So that's very basic in that manner. But now we want to compound it. But before that, we want to disconnect the idea of 2 and 1. So it seems like there is a force. The idea of a force means by construction or by definition means that only when both the charges are there it exists. It is on to by one. Force is always on a charge. But now we want to introduce a concept which is there independent of charge 2. It is a property of 1. Just because one exists, the concept exists. It's very much like gravity. Gravity does not care whether the moon exists there or not. Gravitational field is there just because Earth is there. So similarly, we want to introduce an idea related to charge Q1 alone, and it is very straightforward. Just remove the charge Q2 from that equation. So the electric field now, like gravitational field, this is the electric field associated with the charge 1, electric field. Due to charge 1, as far as mathematics goes, it is straightforward, just remove Q2. So you are dividing out the idea of force from the expression for the force if you want, divide out the charge Q2. And that basically gives you K times Q1 over R squared times R hat. But conceptually, it is much more than just dividing out by Q2. Now you have associated a concept related to charge Q1 alone. That means even if this does not exist, even then the electric field of charge Q1 is there. But you then ask, how does the position of Q2 come into picture? It doesn't matter. This quantity is there everywhere in space. Any point out. It is a physical entity which is there everywhere in space. Just because the charge exists, there is an electric field all around it. It is much stronger closer to it and much weaker further from it. Exactly like gravity, gravitational field is there associated to Earth everywhere in space. However far you go, the gravitational field of Earth exists. It might be very tiny. For all observational purposes, it might be so tiny that you can make it zero. But even at a very large distance, Earth gravity exists. It's very tiny, but it exists. Same thing here. Unless you go all the way to infinity, electric field of a point charge exists everywhere around it. And we will show a big concept you want to take home in this whole semester is that this quantity has energy associated with it and momentum associated with it. Everywhere in space. So charge Q1 exists here. There is no charge here, but in that small volume of space, there is energy and momentum simply because the charge is there exists, just because of the charge in there. And that's what we, in certain forms, that's what we experience as light. Light is not a matter form. It has electric field associated with it. It has magnetic field also. It's a more, it's not static, to be more precise. Light is not static phenomena. But an example is that there could be energy and momentum associated with just a spatial entity sitting somewhere in space. That's what we want to take in from. But most of the problems, it will be sufficient for us to think of it as force per unit charge. So what is the electric field at this point? Remove the charge Q2, and whatever is the force that will be exerted on a unit point charge is what electric field is. So mathematically speaking, it is very much like a force, but conceptually speaking, it is not at all like a force because force requires two charges to act on, but electric field is that for a single point charge. Having introduced the idea of electric field now, and since we have already done the mathematics of forces, we should be able to extend those things in the context of electric field. So let's talk about how can we generate electric field in itself. So let's talk about 2-point charges. Two charges is good enough, but point charges, let's say. And last time we talked about 2 positive point charges. This time, let's talk about 1 negative and 1 positive. The negative charge there and the positive charge. Let's have the reference line connecting them as a horizontal line, which could be the x-axis, and the distance between them, let's say, is 2 times a. That way, we have the y-axis could be the bisecting line, and somewhere here could be your observation point. So let's say that's y. This is a, and that's a. Any configuration that has equal amount of charge, Q here, Q is negative, Q1, which is negative Q, and that's Q2, which is positive. They are the same amount, there is the same amount of charge on each of these charges, but they are opposite in sign. A configuration like this, which constitutes of 2 point charges, one is positive, one is negative, is called a dipole moment. This is called a dipole. Add the word electric to that. Everything that we deal with will have a very similar idea later on for magnetism. So that is what is called a magnetic dipole moment. In fact, what is a magnetic dipole moment? Have you guys come across that before? Idea? Magnetic dipole moment. That's a magnet. Okay, a magnet that you hold in your the refrigerator magnet. We typically say it is a magnet. The property that when you bring in 2 magnets together, what is the property that interacts with each other? That's the magnetic dipole moment. Here we're talking about electric dipole moment. In magnets, you will think of this as a north pole and a south pole. Right? The north pole and the south pole is what a magnet is. It's the same idea here. It's just we are doing the electric version of that. Most of the equations remain the same, but there is a significant difference between the two as far as the sources of magnetic field and electric field goes. But conceptually or mathematically speaking, there is a lot of similarity in certain senses, but there is a lot of differences too. Okay, so that's your configuration. We just call the electric dipole moment. Another reason why electric dipole moment is a very important concept is most of the atoms are neutral. Right? There is no electric charge on them. So when 2 atoms are kept together, there are no electric forces on an average. The forces between them is because of electric dipole moment. The charges are not exactly distributed spherically symmetric. There is a small asymmetry in that. If there is an asymmetry, then the asymmetry of one charge, which is the measure of asymmetry, is the electric dipole moment. The electric dipole moment of one atom interacts with the electric dipole moment of the other atom. So atomic interactions are slightly harder because electrostatic equations don't exactly immediately go through. You have to do more than because there are more than one charge on it. Mostly they are neutral. So this is, if you want to think of it, this is an atom where the center of the positive charge is slightly displaced from the center of the negative charge. And this is an observation point now. This is an observation point. That's your point here. So if you remove the charge Q2, you can still define a concept called electric field. Electric field is a property of a coordinate in space. And everywhere in space, there is an electric field just because the charges exist. So this is the observation point. So what will be, if you were to talk in terms of force, you calculate the electric field here and then multiply it by the third charge. Charge times the electric field gives you the force. So let's calculate the electric field here. The negative charge, even though we are saying this is a point, we have to pretend that there is a unit positive charge there, and we get the bracket, so the electric field will be in this direction. So that's E1. Along the line connecting the observation point and the charge, it is towards the negative charge, and the electric field due to the positive charge is going away, and it is in this time. These two lengths will be the same because the charges are the same, and the distance between the observation point and these two charges is exactly the same. So that's EQ. That's EQ. Once you have the electric field, as far as vector nature goes, they behave exactly like a force, mathematically speaking. So there is a y component here, y component here. These two cancel out. So I do not have to worry about that because the magnitude will be exactly the same. If this is the same distance, these distances are the same. The symmetry of the problem, the y component exactly cancel out, and the x component adds up. So the total electric field due to the dipole, the total electric field due to the electric dipole will be equal to E1 plus E2. And we said that the y component immediately cancels out. Let's say this is angle theta. If this is angle theta, that's angle theta, and this side here will be sine theta, that's opposite to the angle. So the x component is sine theta. So we have E1, it's in the minus I direction. And it is 2 times the magnitude of either one of them. So that's E1 I pick times the sine of sine. Okay. So this is a vector equation. Using symmetry, I argue that the y components will cancel each other. So I argue that it is only in the negative I direction that it contributes, and it is 2 times E1 and so sine theta. And what is E1? We use the electric field idea, so that's minus I times Q times E1 is K times Q. I should say this is the magnitude of Q because I've already taken care of the sign here. When I say that the electric field is the minus, I directly taken care of the sign divided by R squared. That's my magnitude of the electric field. R squared is the distance between these two, between the observation point and either one of the charges. R squared, so this is R squared, the distance between the, which is y and an a, right? So this y squared plus a squared. Let me write this as R squared. So this one. What I find in this diagram. So that's y. This is R, this is a, and the angle here. Theta y. These two are the given parameters, and R is I just constructed it so that I can use that temporarily, and theta also is a temporary parameter. This is the two quantities you want to write your expression in. This is the, like when you say a dipole, it is you think of it as a distance between the two charges gives you, that's a parameter that defines the problem, and how far you are from the dipole is given by y. R and theta are temporary parameters that you you created at this point. That's your E1. I'm still left out with sine theta. Sine theta is the sine opposite over hypotenuse, but A over R. A over R. All this, each of these ideas should be straightforward. This is your vector equation, E1 plus EQ. Use symmetry to come to conclude that it is 2 times the x component of the electric field. And the magnitude here is where you use Coulomb's law, and that's geometry. Sine theta, the x component is sine theta, that's A over R. And that's equal to minus I hat. And K stays as it is. And you have 2 times A times Q. Divided by R cubed. That's your electric field due to this configuration. I wrote this, I intended to define this electric dipole moment. Whenever you have a charge separated, or 2 charges, one is positive and one is negative, separated by a distance a, the electric dipole moment is defined as P, is defined to be the distance between them times Q. So Q times the distance between them, in this case it is 2 times A. So this whole thing is the distance between the charges. Maybe it is better to write this as D and then replace it with 2 times A. So this is D, where this is the distance between them. In my configuration, it is 2 times A. And this is just the charge multiplied by the position of the positive charge from the negative charge. Once you say it is a vector, it matters whether it is from negative to positive or positive to negative. It is always from the negative to positive. So that's your P. So electric charge is the basic entity in masses. This concept doesn't come in because you usually have only positive charges. The idea of an electric dipole moment is how much off you're from spherical symmetry. If you have a positive charge, a lot of positive charge, there is a center of positive charge. There's a lot of negative charges, there's a center of negative charge. If they are exactly on one on the other, then the electric dipole moment is zero. If they are not, how much they are separated by, that defines your electric dipole moment. In masses, there is no electric dipole moment. What you have is an electric or quadrupole moment. It is not a electric at all. It is configured using mass. And there is no electric or the dipole moment graph. For mass, there is no dipole moment because there is no negative mass. If there was an idea of a negative mass, then you would have associated a dipole moment for gravity in the context of gravity also. So electric dipole moment and magnetic dipole moment do not have an analog in gravity. In this case, once you have this scenario here, so it is I is positive, so this is equal to minus K D over R2. And I should clarify that this is on the y-axis. I did not really analyze the problem anywhere beyond this. It's slightly more complicated away from the y-axis, but nothing that we cannot do. We can technically do that. It's a little more tedious, not very tedious. So for a point charge, it is 1 over r squared. For a dipole, it is 1 over r cubed. What is that? A dipole has a distance in the numerator, so that is an extra distance in there. The next concept that comes in is when there are 4 charges, 2 positive and 2 negative. That's called a quadrupole moment, and that will have the next power in this configuration. You start from r squared, r cubed, and so on. That you can build a whole series on that, and we will stick only to electric dipole moment, primarily because in atomic interactions, this plays a very important role. We have 2 charges. We can put in 3 charges, 4 charges, and we can create an electric field here. And then we can talk about what will be the force exerted on a charge at this point. Notice here there is no charge as of now. This is just a point in space. So what will be the force on charge 3? So let me so force on charge Q3 placed at the observation point is, let's say this is the force on charge 3, so that's F3. Force on charge 3. It is Q3 times the electric field at the observation point, which we calculated is the total electric field. So this is the electric field at the observation point. So force is always charge times the electric field. This should be compared with the gravitational force is equal to mass times the gravitational field. We typically stay on the surface of Earth, and then this is 9.8. But that need not be 9.8. It is different in different places at different spatial points. but it anyway is equal to mass times the gravitational field at the position of the mass. Here it is the force on an electric charge Q3 is the charge itself times the electric field at the position of charge Q3. So that's the connection, that's the basic idea. And this equation should be what you should be using. Always calculate the electric field, then talk about what's the force exerted on a charge due to the electric field. So let's calculate a more complicated electric field, especially if there are a lot of charges. We know integration, so we should be able to put in a lot of charges along the line, and we should be able to get the total electric field from all the charges together. Any questions or comments at this point? This might seem very abstract at this point, and if you want to connect with what you see around yourself on a daily basis, force is always connected to potential energy, right? So when we think of gravitational force, that is mg, and the moment you have that, you can talk about mgh. How much is the potential associated with a mass that is at a height h. Similarly, this curve contributes to the electric force, electric field contributes to the electric force, and electric force has an electric energy associated with it, and electric energy is the voltage that we talk about. When you say that is a 3-volt battery, that's the energy associated with this force. So now we are introducing the idea of force. Very soon we will talk about the energy associated with it, and then we will talk about devices that can be used to generate that energy and perform some useful work out of it. So that will be the chronology of events that will come in: force, electric energy, and then talk about devices that make many of the things work around us. So let's talk about electric field. You do a long thin rock. So let's think of a very long stick, metallic rod, let's say. Since we want to have a charge on it, it's easy to have a metallic rod. So this is very thin for our purposes, and it extends all the way to infinity. These 3 dots mean that they extend all the way to positive infinity, and the same thing on the left side. They extend all the way to negative infinity. This is really thin, so infinitely thin if you want. You put a positive charge on it. So let's say you distribute positive charges on it, and you uniformly distribute it everywhere on the rock. And we would like to calculate what is the electric field at this point. The moment we introduce the idea of electric field, it is a property of a spatial point. Everywhere around here, there is a positive charge, electric field due to these charges. And we would like to know what is the electric field at this point. But once you know the electric field at this point, it must be the same at this point also, because this is infinitely long, it's symmetric. So once you know the property at this point, it must be the same here, and it must be the same everywhere at the same distance A. It gets weaker as you go farther, but you would like to know how does this get weaker? For a point charge, this is 1 over r square, but is it the same when you have a extremely long thin rod? So we want to do this using the basic idea of a point charge. So we break this into tiny elements of charge. So this tiny piece is a point charge, and we know the electric field due to that. Right, so that's your source, and this is your observation point. Observation point. Let's have a reference set. That's your, and this could be x equal to 0. That's your x. And let's say this tiny distance here, let's say is dx. So at a distance x, there is a tiny element of charge which is contained in the length dx, and the amount of charge on this is, let's say, dq. Remember, in calculus, whenever you introduce d in front, it means it's infinitely small. You can take the limit, it's going to 0. So this is infinitely tiny length, and this is an infinitely tiny charge. Even though it is infinitely tiny, we are adding up a lot of them. There is a continuous distribution of these infinitely tiny charges. They are, even though they are extremely small, there are so many of them. When you add up together, that could be a finite charge. You're saying this is uniform charge on this. So uniform definition means that how much ever charge length you take divided by that, it doesn't matter which length you take, it is always the same. So dq, the charge per unit length. So the charge per unit length for any length is the same. That's what it means by uniform. I could say 1 meter of this rod and ask how much charge is there, charge per unit length, and that will be the same. And let's call that lambda. So this is charge per unit length. This is charge per unit length. That's necessary because the total charge on this rod will be infinity. If the length of this rod is large, that's infinity, then the total charge will be infinity. Total length is infinity, but that ratio is still finite. And if you're not comfortable with infinity, what we are talking about is, or practically speaking, how do you construct infinite rods? This is a very long rod and has a very large charge. Experimentally speaking, if we are 2 centimeters from here, if this was 20 centimeters long, to 10% accuracy, 20 centimeters is infinity for 2 centimeters, to 10% accuracy. So we talk in terms of errors here. If we are fine with 10% error, 20 centimeters is as good as infinity for 2 centimeters. So that's the way we are talking. So infinity is okay. It is experimentally is achievable to a certain accuracy. Within 10% accuracy, we can achieve a very so that's the idea of uniform charge distribution on a rod. And we would like to know the electric field here. So let's talk about this particular tiny element. That's a point charge. So for the observation point here, we know it obeys Coulomb's law. So Coulomb's law says that the electric field at this point will be, if this was a positive charge, it will exert a force in this direction. This is a tiny charge in a tiny length, and it will create a tiny amount of electric field, and that we will call is dE. Remember, in calculus, anything that is infinitely tiny, we give it a name differential. So it is a small tiny electric field, and we label it as B times E. Let's say this is a distance A. That's what we are calculating the electric field of a uniformly charged rod at a distance A. This could be anywhere. There's a circular symmetry to this wire. So this point could be anywhere around that rod. So let's calculate what is dE using Coulomb's law. It is K times dQ. Instead of talking about a single charge, so that's a tiny, infinitely tiny charge dQ over the distance. The distance is x. That's A, so that's x squared plus A squared. X squared plus A squared or R squared. That's x squared plus A squared. That's the distance squared, and then you want to square. Or I think it's easier to just write that R. But you'll have to convert it into x squared plus A squared very soon. So if it helps, if it is less clutter, this is R squared. But that's just the magnitude. We also need to calculate the direction of that. So that's R hat. And this R hat is the direction of this quantity here. Let's say this is angle theta. That's angle theta. That's sine theta. Sine theta times I hat plus the sine theta times j hat. So this is equal to R hat is sine theta times I hat minus, because it's the second quadrant, plus the sine theta and the j hat. For every element on the right side, now there is a positive charge we are talking about, that is a corresponding element on the side, which will have a force on this direction. So last time for a dipole, because it was positive and negative, the two vertical components cancel. Here it is the horizontal component that is canceling. So it is the vertical component that will add up. But I won't do it 2 times, but instead I will do the vertical component add up from negative to positive. So this does not contribute. This goes to 0, cancels. Cancels for total. One can do that, and that integral will come out to be 0, but we will just simply use the symmetry condition for. So dE is then, I pull out the j hat, K dQ over R squared, and cosine theta is nothing but x over R. X over R. That's R cubed in the denominator. So again, the idea of the vectors that we have used a lot in the earlier semester, that leads us to this equation. That's vector addition if you want. Using symmetry arguments, you argue that the x component does not contribute. That means this cancels this piece, and the y component, I want to add up all together. If I want to get a complete contribution from all the charges, I want to add up all these charges, a contribution from all these charges. So the total electric field will be the sum of, which is integration of all these tiny electric fields. This is integral of dE, which means it's the sum of all contributions from all these tiny charges. And that is the same as do the same sum here. And that is equal to integrate. J does not depend on this integral. J times K and an integral over dq here is nothing but lambda times dx. Let me put the lambda here, constant dx x over r squared. Yes, Christian.
Should there be two?
Two.
Like, with
yeah.
and
Good question. In the last example, we said there are two pieces here, right? The argument is that, oh, there are two pieces here, there should be two times that. That's the point. It depends on how you're counting. If I'm doing two, then I should go from here to there. If I go from there to there, then this will be counted two times.
Okay.
Is that clear? So either way is okay. You either go from 0 to infinity and have a factor of 2 in it, or you go from minus infinity to plus infinity and not have the factor of 2 in it. Either way, this integral, it will be nicer to have go from minus infinity to plus infinity. Good point. That's a good clarification for everyone. Why was there not a factor of 2 that came up in the last example? So it is coming right at the stage here. I have to put the limits here. So this is x equal to minus infinity. And this is x equal to plus infinity. And notice how I changed from charge, it was a dq. dq became a dx because it was uniform charge distribution. If it was not a uniform charge distribution, that would not have happened. X is already there in the numerator and the denominator, that is an r cubed. R is x squared plus a squared. We have a squared plus x squared raised to 3/2. That's an integral that is doable. Probably you're already familiar with that, but what is that equal to? So let's quickly do that here. So this is an integral going from minus infinity to plus infinity dx x over a squared plus x squared. Sometimes you can just look this integral up and in the standard integrals you have an answer, but this is using simple substitution. You can immediately do this. Let's substitute x is equal to a times what the substitution you would use. Use your integrals if you have any substitution you can suggest. How many of you have done integrations? Sure. Yeah, that's okay. Yeah, if you don't know, it's okay. So this is tangent theta. Whenever you have this construction positive in the positive construction of a squared plus x squared coming up, we substitute a times tangent theta, not tangent squared. And that's because 1 plus tangent square theta. We have this identity secant square theta. So when you substitute this quantity, this becomes 1 plus tangent square theta, which is secant square theta. There is also this feature that if you were to differentiate this, the x is equal to a times secant square theta. So you use all these features in there, right? So there's an identity here from trigonometry, which is just a version of sine square theta plus cosine square theta is equal to 1, written in terms of tangent and secant. Substitute this substitution means I'm changing the variable from x to angle theta. Algebraically speaking, when x is equal to minus infinity, tangent theta, when is it minus infinity, you ask? You remember that tangent theta curve that goes like this. It is minus infinity when x is equal to minus pi by 2. So that's one way of looking at it. Algebraically speaking, when x is equal to minus infinity, theta is minus pi by 2, and x is equal to plus infinity, it is plus pi by 2. And that's coming from this equation. But you can also use geometry here. This is your x. And if x was infinity, this point is very much to the right. So if you were to think of this triangle here, as you pull this point to the right, this angle starts opening up, and all the way to the right, this angle theta becomes pi by 2. So that's the geometric way of looking at it. Either way, you argue that this minus infinity corresponds to minus pi by 2, and this plus infinity corresponds to plus pi by 2. Either algebraically or geometrically. Dx is dx is x a secant square theta d theta, and I need to check my equation. Yeah. Check this equation here. This was cosine theta. Here, this cosine theta gave you x over r. Cosine theta is not opposite to the hypotenuse, it is adjacent to the hypotenuse. Right, so I made a mistake here. So this should have been A. Please correct that. So this should have been A. So this is A. Very sorry. This should be A, which means this here is A. So this was an X, I changed to A. I corrected this. This was an X earlier. I made this an A. That makes this A here. And there's already an A here, so this becomes A squared. And the denominator, you have A squared plus 1 plus tangent square theta, that's secant squared. That makes it secant cube. That's A cube times secant cube. This is an easy integral now. Secant square cancels with 2 of them in the denominator. Remember, secant is 1 over cosine. So this is 1 over A. A square cancels this. And this is minus pi by 2 plus pi by 2. Secant is cosine theta d theta. And that should be very elementary integral. Cosine theta integral is sine theta. That's 1 over A sine theta, evaluated from minus pi by 2 plus pi by 2. Sine of pi by 2 is 1, sine of minus pi by 2 is minus 1, but you're subtracting minus 1 from 1, so it is 2. 2 over A. It's very simple result. Let's just say that this integral is equal to 2 over A. Take it all the way there, and this becomes the electric field now is J times k lambda as a factor of 2, so put it here and divide by 8. That's what you want to keep in mind for a thin electrically charged, uniformly charged rod. The electric field is not inverse square relation, that is an inverse relation in distance. So let me clarify this. So we have a point charge. Its geometry is just a sphere of infinitely tiny radius, and its electric field is in the radial direction, and it is k times q over r square. That's charge q. It gets weaker and weaker as you go farther and farther. It is 1 over r square dependent. So as you go farther, the field gets smaller by 1 over r square dependence. Now if I am talking about uniformly charged rod, the thin rod, geometrically speaking, this will look exactly like this. If the rod was coming out of the plane, it will look exactly like this, a cylinder. This is sphere of r going to 0. Now I'm saying this is a cylinder of radius going to 0. Again, look, the thing, if I were to make it come out of the board, but if I were to make it horizontal, this is what we are talking about. And now, since it's a cylinder, I cannot talk about the charge because that will be infinitely large. So I have to talk about charge per unit length. Lambda is charge per unit length. And the electric field is still radially outward, right? The direction was j hat. It was perpendicularly out. If I were to view it from that side, it is radially out, so radially outward. And now it is 2 times k times lambda over r. So the point is, if I want to, just because I stretch the charge uniformly along one line, I got rid of one of the distance dependence in here. And that leads to the idea that what if we had a thin plate? And that will look like a positively charged plate, infinitely. And we ask, what will the electric field be? Notice R square for a point charge, for a line charge, this is 1 over R. Any guesses what will be the electric field for a planar, large, infinitely large plane? R square, R, what might be the next one? They're going down, right? 2, 1. There's a 0 in between, right? 2, 1, 0, right? So this will be R hat times some k constant, But R raised to 0, there is no R dependence. No R dependence, right? R raised to 0 means this is not that, this is 1, right? So that means this is constant. Right? And that should not be very surprising if you were to think of gravity. When does the gravitational field become constant? When you're very close to Earth, that means Earth is flat. For our practical purposes, when we are dropping a mass, Earth is pretty much flat. If I were to go very far from Earth, then gravitational field is not constant. So similarly, when we have a flat, uniformly charged plate, then the electric field due to that will be a constant. And we will, mostly in the lab, whenever we want to work with electric field, we will work with flat plate. So we want to come up with that. That's the next goal. And then we will do dynamics. Then we will put charges on that. Once you have uniform electric fields, that's like uniform gravity. It's easier to deal with. You don't have to do so much integrations and mathematically significantly simpler to deal with. So we will derive what is the electric field we do. Flat plate, and then do problems related to dynamics. We'll put a chart in there. Thank you. Is this get recorded?
I believe so. I end it. Yeah. It's-